Hello and welcome to BioRules video lessons. Today we are going to be talking about population ecology. So population ecology is ecology of how many organisms are there in one species. We saw many factors that are going to be influencing this. We discussed lots of stuff in the previous lessons, but now we're going to take a closer look on the population, especially on population growth and decline, stabilization, something like that. Okay. So first thing, what causes a population to change? Natality, that puts population, individuals in a population, it increases population. And the mortality that removes individuals from a population reduces the population. In the same way, immigration toward the population increases the population, and emigration away from the population reduces the population. So ultimately, these four factors are the ones that are going to be determining the growth of a population. Okay? If natality and immigration equals to mortality and immigration, then the population is not going to be growing. So whenever natality plus migration equals mortality plus immigration, the growth is going to be equal to zero. The population stays stable. So let's take a look on one simple example of populations. One bacteria. If we put one bacteria in a petri dish, each bacteria is going to be reproducing every generation. There's plenty of resources. They have enough just for every generation. They divide in half and they make one bacteria makes two bacteria. So let's take a look on how things are going to happen. A table on the left, a graph on the right, and let's visualize how is this population going to grow. So generation 0, the population equals 1. We said here we are putting one bacteria. So what is going to be happening in generation 1? Generation 1, every bacteria reproduces, makes two bacteria, so I should have here two individuals. Ooh, look, the graph over there. The population is growing. What will happen in generation 2? Every one of those two are going to be dividing, making more two. So 2 is going to divide and make 2. We are going to have 4. Oh, look, the population is growing. So what will happen in the next generations? Is the population going to keep growing like this? Or is it going to be growing a different way? What do you think? Let's see. Let's put a number here. In the third generation, every one of those 4s are going to be reproducing, and they are going to end up making 8. And in the fourth, 16, and then in the fifth, 32, and then 64, 128, 156. Ooh, look at this graph. This is not a linear growth. What is happening here is that the population is growing, and is growing faster every time. And the definition for this is exponential growth. Now it looks like a J, and it grows exponentially. It means that every time it's growing faster and faster and faster. For every generation here, we're going to have much more than we had before. This is a typical population growth when we have the beginning of a population, when we have lots of resources and not many natural enemies. Okay? And the formula for this here was 2 to the power of n. This is the one that we played here. The exponent here actually was generation. Now we did this on purpose just for you to visualize. This population is growing to a certain exponent. In this case here, the number of the generation. Okay? So, question. Natality is much bigger than mortality, or natality and immigration much bigger than mortality and immigration. So in this case, we have an exponential growth, right? But for this to happen, you need to have plenty of resources, lots of resources, no or very low competition, because if there's plenty of resources, there's no competition. You're going to have no or very low predation. Okay? If you have very few organisms, it doesn't manage to maintain the predator population. But as soon as the population starts getting bigger, then the population of the predator may start growing bigger. The same for diseases. Now, if you have a low population, you probably don't have much disease, but the more the population grows, easily the disease manages to spread around. So this here is what is expected to happen for an exponential growth. Now, natality and immigration much bigger than mortality and immigration, and that will only happen when you have plenty of resources and no or low natural enemies. Okay? The question is, can a population grow exponentially forever? What do you think? Yes? No? So let me tell you this. If you give enough resources to a bacteria, no, make a colony of bacteria, and you give enough resource for that, in 13 days, multiplying every around 1 hour, 1 hour and a half, making about 7 or 8 generations a day, that bacteria population will have 10 times the volume of planet Earth in 13 days. So that's quite big. And actually, in 42 days, it will have the volume of the entire observable universe. So actually, that's not possible. A bacteria growing on planet Earth cannot grow to become bigger in volume than the volume of planet Earth itself. Of course not. That's ridiculous. So what's happening here? A population cannot grow indefinitely because there will be at a certain point competition for resources. There will be at a certain point predators that will follow the prey population. There will be diseases that will be spreading and thriving. So actually, populations grow exponentially in the beginning, but later on, they don't manage to grow exponentially anymore. So how are they going to be growing? This brings us to another curve. We saw the exponential growth. Now we're going to be talking about the logistic growth, also known as the sigmoid curve. So in this case here, the population is going to be growing. I will start with a small population just to exemplify our stuff here in the beginning. Now you have exponential growth. I start with a very small population, so it grows exponentially. We saw that before. If you have a small population, you have lots of resources, plenty of resources, exponential growth. However, at a certain point, the resource start becoming limited, or predators start to grow the population. So this starts slowing down the growth. So we get to the transition point. So when the population starts to struggle to keep growing, it grows, but grows slower. So there we have the population is still growing, but now it's not growing exponentially anymore. It starts growing more linearly, and even now stabilizing and getting reducing this growth, but it's still growing. And it grows all the way to the point when competition gets fierce and when natality equals mortality. When natality equals mortality, then you reach the plateau, which means no change. So that point over there is the plateau where you have not enough resource for the population to grow, just enough resource to keep the population stable. Natality equals mortality. Simple as that. Okay? So, a closer look on the sigmoid curve. The first part is the exponential growth, then the transition, then the plateau. Okay? And the plateau actually reaches a certain value that we call the K value. K for carrying capacity. Okay? That is the maximum capacity of that population with those circumstances that are there. When are we going to have the exponential growth? When resources are plenty. Lots of food, lots of space, enemies are low, not many predators, not many disease, and the growth is, the population is growing and the growth is speeding up. The more it grows, faster it grows. And then you get to the transition. Resources and or enemies start to show effects, start to show their impact. Okay, the population still grows, but the growth now slows down. And then we reach the plateau, where you have a struggle for survival that is very big. You have lots of competition for resource or many enemies. And at that point, natality equals mortality. That means one gets born, one must die. So this is when you reach the plateau and you reach the carrying capacity. So the population stays there around the carrying capacity. This is the sigmoid population growth, which is a more typical population growth because it's density dependent. The growth depends on the density of the individuals. Exponential when the density is small, and no growth when the density reaches the carrying capacity. Okay? So, what's going to be affecting population? of course, we mentioned resources. No food, shelter, territory, time, sometimes a resource, and also enemies. No predators, parasites, competition with other species, okay, and of course, which is related to resource and enemies, competition by the same species. That also limits the population growth. Okay? There are two extreme strategies when you talk about population strategies. Okay? Actually, there are many strategies around, but usually we illustrate extremes here. So one extreme strategy is populations that invest in growing the population very fast. Okay? So species that have a very high reproductive rate, that strive or that do well in new environments full of resources. They enjoy resource surplus, and a good example of that is rats. So they find a free place, they have their full of food, they have many babies, and they move away when things get ugly. If you watch Ratatouille, when things start getting bad, the rats moved away and they went to Paris. That's the idea of this strategy, okay? They like unstable environments that you have surplus of resources, and then not so much, and then surplus, and then not so much. And the name for this strategy is R strategist. Why? Because the population grows to a certain exponent. So in this example here, if the population grows exponentially with an exponent r bigger than 1, the population will grow exponentially all the way when it gets to a certain point that, hey, too much resource went out, and then the population crashes. And then they run away, like Remy and its friends in Ratatouille, and they went away from the farm to the city to try to grow the population again. Hey, things crash, and then they run away again, and the cycle carries on. Okay? Our strategies are typical animals that invest this. A good example among mammals of our strategists are rats. Okay? So our strategy, what's the idea? If you plot their time for population, you find a new place full of resources, you grow your population, and then you grow until you exhaust the resource, and then the population crashes. Resource exhaustion, you have a high mortality and or immigration, and then, find a new place, lots of resources. And then the population grows back again, and then they spread over again. This is the typical strategy of an R strategist. This is what we think about rats. Okay? An opposite strategy here that goes to the other side of the spectrum would be for species that invest in competing for resources. They have low reproductive rates, they have parental care, they take care of the babies, they have few babies, but they take very good care of them. Okay? They do well in stable environments because they compete for the resource. They fight for the resource. And a classic example among mammals would be elephants. Elephants are typical strategists on this extreme strategy here. Okay? They keep the place and territories. They have few babies, but they care for them. Okay? They like stable environments. And the name for this is K strategists. Why? Because they like to live around the carrying capacity. So population grows, they reach carrying capacity, and they stay around the carrying capacity. So putting it all together, this is the idea here. Population is around the plateau on the carrying capacity. Then it oscillates, now maybe going a little bit up, a little bit down. You have an eventual oscillation, but the population stays there, is struggling to stay in the plateau. This is the K strategist. Just remembering that R strategists and K strategists are comparison of strategies of similar groups. So you can compare rats to elephants. But a rat that's a K strategist comparing to an elephant will be, the rat is R strategist compared to an elephant. It will be a K strategist if you compare it to a bacteria. So we only compare K strategists or R strategists among similar organisms, mammals with mammals, plants with plants, and so on. Okay? Here now we have another idea, that is how populations are controlled. There is top-down population control. This is a classic where the predator controls the population. So, for example, The population of sea urchin is controlled by its predator, the sea otter. We saw this here in an example before, the keystone species, right? We have a food web here. Let me speed this up. We have algae, macroalgae, we have phytoplankton, and these guys feed other organs, so herbivore and invertebrates, no large crabs, zooplankton, sessile organs. So I put a full food web here for you to see. This is the food web, sorry, there's one more here, the food web of kelp forest, and there they are. So the sea otter actually is keeping in check the population of other animals like the sea urchins. And actually the shark is also keeping in check the population of sea otters. So the sea otters are being top-down controlled by sharks, the sea urchins are being top-down controlled by sea otters. Okay? If we remove the sea otters, then we might have some problems. So for example here, I'm putting the same food web over there, but what happens if we remove the sea otters? So one thing is that there will be a bottom-up regulation of the sharks. The sharks get controlled by their food. This is bottom-up, I will show that in a moment. But with no sea otters, now the population of sea urchins explodes, the sea stars population explodes, the crabs and the large fish also explode. As a result, they start preying more on its food, and they end up over-exploiting the kelp and reduces that kind of interaction over there. And that is going to be increasing the sea urchin predation on the sessile invertebrates, which is going to be reducing the population of those guys as well, which is going to be changing the entire ecosystem over there. So this ecosystem here is typically top-down controlled. If you have lots of predators, the population of everything stays within certain controlled boundaries. Examples can be the opposite, bottom-up population control. Bottom-up population control is when the population is controlled from the bottom, by the food, not by the predator. Typical example of that, algae in the ocean. If you have lots of sunlight, there will be algae, and the population is going to be growing, but no, the grays will be there, the fish will be there, and the birds. But if you have a lot of phytoplankton that the grazers are not going to be eating very much, or the fish, what will happen is that the algae will suffer, because the phytoplankton will make shadow, then the fish will suffer, and if the fish suffer, the birds will suffer as well. So in this case here, we have a bottom-up population control. And a very good example of a bottom-up population control is the one that I have already shown you twice at least. The number of trophic levels in an ecosystem is related to the amount of light. So in a tropical rainforest you have lots of light, then we can have lots of productivity by plants, so lots of plants are going to be making very long food chains. So you have there 5 trophic levels. But in a taiga, where you have less productivity, you're going to end up having less trophic levels. And if you have a desert with even less productivity, you're going to end up having only 3 trophic levels. So the more productivity, more trophic levels. So that means more species, more population that is going to be there. So this is a good example on how a bottom-up regulation of populations can happen just because of productivity, just because of light and water. Okay? Now I have a quick questionnaire here for you to show that you have learned everything from this class. I hope you had fun. I see you in the next class.